Boom. Okay, this is in chapter 7 of the physics class, the second part. Conservative forces, potential energy is a conservative force. So a rock on top of a hill has a certain amount of potential energy that it can release. Winding a clock spring has potential energy that we consider being released. There is actually some stress, some heat, everything else that's actually lost. But physics is about simplifying things, and if you can simplify things without adding a lot of error, it's often done in order to get the concepts down. So here's spring constant, and they're turning it into, springs have potential energy. Guitar. If I have conservative forces, my potential energy and my kinetic energy are conserved using only conservative forces. Okay, so your potential energy of a boulder that's at the top of the hill not moving, as it goes down the hill, that energy will turn into kinetic energy based on its velocity. So at any point in the system, the energies will add up. So that's one of the simplifying things we do in physics in order to kind of steady things. And we do lose a little bit. What they're illustrating here is a toy car. It doesn't matter what path you take. If it gets there, it has to gain a certain amount of potential energy. And so your kinetic energy and your potential energy initial has to equal your kinetic energy final and your potential energy final. And we look for systems that we study and we go through and we make sure that that is the case. However, there are non-conservative forces. We have things like thermal energy. We have things like noise. So heat, sound, and deformation of the ground, thud, kinetic energy. So in energy is always conserved, but it does change forms. So what we're trying to do here is we're trying to say that kinetic energy to potential energy, we get a nice smooth transition. And in some systems that works pretty good. In other systems it doesn't work so well. This is a good problem. If I'm pushing a crate up a ramp and I have to give it a force and I've got a frictional force going back against me, then the steeper the ramp that I'm pushing up, the more force I have to use. So if you're by yourself and you're trying to load something on a trailer, if you can make your ramp longer, then you have to apply less force. Now you're doing the same amount of work because you're increasing your distance, but you would reduce your force. So that's a good little problem that I'd like to incorporate. But generally in physics, we pick systems where kinetic energy turns into potential energy. And energy is always conserved. Now, here's all your energies. Here's your other energies. And these are non-conservative works, other energies. And so what we try and do is we try and minimize our non-conservative and our other energies, such that we can say KEI plus PEI is KE final plus PE final. A boulder rolling down the hill. Yes, it's going to make noise. It's going to hit trees. There's going to be noise. It could generate some heat. It could deform the ground. Those would wind up being other energies. So we want to pick systems where we don't have to account for that, and then we can sort of study this, the conservative forces, the KE and PE, being conserved. So a lot of the systems you'll see in physics are kinetic energy, potential energy only, and we ignore the effects of the other, because you're always going to lose something. Always. And if you consider all the energies in a system, then everything, energy is conserved. Your energy at the beginning is your energy at the end, even if you're losing some heat or whatever. Efficiency equation is work out over energy in, needs to be in the same units. So you can talk about the efficiencies. Power is work over time, or work divided by time. So work is force times distance. And if I take force times distance and divide it by time, I wind up with a power. And the SI unit for power is watts, which is generally associated with electrical. But if work is force times distance, that'd be a Newton meter divided by a second. It is also a watt, so a watt would convert back into mechanical. So there's a conversion between electrical and mechanical. And then he got some problems. Horsepower. In the English system, we use horsepower, and so we want to be able to convert it to SI. This is an excellent one to remember, and I think I've asked a problem about it. I do in other classes. That's a good one to keep in the back of your mind. And kilowatt hours is I'm doing so many watts for so many hours. So energy is power times time. So I'm getting so much out. Work energy in humans. So somebody's made a table about how efficient we are, how much energy we consume. World energy use, petroleum, coal. You see that that's most of it, and natural gas. So most everything is fossil fuels. And we've got this little bitty slivers of hydroelectric, nuclear, and geothermal, a little piece of the pie. And energy consumption in the solar fields. So that's going to be pretty much 7. Now, probably find what worksheet we're on and go back through that and talk about it, maybe come back to this chapter. But I wanted to make sure I made some comments on the chapter. So if you're reading, you can kind of go through and follow along. And I thank you for watching.